Linear programming is a way of solving applications that deal with systems of linear inequalities. There's this little twist of an equation that we want to minimize or maximize. So for example, it could be a scenario where we have all of these restrictions, which happens with companies. Like there's only so much they can produce or so much that they can have in terms of costs. But then they might be interested, like, okay, what is the magic formula that will maximize our revenue or minimize costs? Things that are beneficial to the business in terms of maximizing and minimizing. And that's what linear programming uses, is it takes these restrictions and then finds this maximization or minimization in the process. So with these problems, there will be a lot of information provided because we'll have all these restrictions and a thing we want to minimize and maximize and variables and all sorts of things. So something I really try to emphasize is how to grab the information from this block of text and then how do we go about solving, which in terms of solving, it'll be using what we learned with our systems of linear inequalities and then putting a little algebra in there. So let's just talk through kind of this setup without actually solving it, just this word problem and what's coming through. So we have a company manufactures and sells two types of lights. So typically that'll be the case where we have these two scenarios because we'll have an X and a Y. They sell one light with disposable batteries and for $5 and a second light for $10 with rechargeable batteries. So there's our two scenarios, and in terms of information, they're telling us about the cost. They must produce at least 5 lights. They must produce at least 5 lights with disposable batteries, but no more than 15 per day. So we're getting this restriction here. And then the number of lights per day with rechargeable batteries produced must be greater than or equal to the number of lights with disposable batteries. The number of lights with rechargeable batteries produced must be no more than 20 per day. How many of each light should the company produce and sell to maximize the revenue per day? So just to get some information going, like at the beginning here where they're talking about cost, so they sell, not cost, this would actually be revenue. So money that they're making, and we're going to call X the disposable batteries and Y the rechargeable. So revenue is coming from $5 per disposable battery, so 5 times X, plus $10 per rechargeable battery, so 10 times Y. So we're getting an equation for revenue there. Then their restriction for disposable batteries, so produce at least 5 lights, but no more than 15. So that's giving us this restriction that however many value for X we have, the lower bound is 5, upper bound is 15. So X is stuck between those two pieces. Then for the disposable batteries, rechargeable batteries. So with rechargeable batteries produced must be greater than or equal to the number of lights with disposable batteries. So rechargeable is Y, so it has to be more than or equal to X. And then the number of lights with rechargeable batteries produced must be no more than 20. So it's restricted that it can't go beyond 20. So actually Y we could do in a single inequality of saying X is the lower bound because it has to be greater than or equal to X, but can't pass 20. So in the wording, we're getting these pieces, and as you can see, these pieces are showing up down here with this R equals 5X plus 10Y. We have this 5 is less than or equal to X is less than or equal to 15. And then this was separated, but it could have been all together that Y is more than or equal to X and Y is less than or equal to 20. So we end up with these inequalities, which are kind of causing these restrictions. Really, our terminology will be constraints. So those are the constraints, all of those inequalities. But then let's look at the actual question that they're asking. So we want to know, how many of each light should the company produce and sell to maximize their revenue? So there's going to be wording in terms of minimizing or maximizing. So we want to maximize this revenue function, so this 5x plus 10y. This is called our objective function. So that's going to be what we want to minimize or maximize. And what we want to do is, working within these restraints, we want to maximize this objective function. And at the end, what we should be getting is an answer that tells us an exact value for x and an exact value for y that works within these constraints and maximizes that linear equation. We're going to do quite a few examples with these, and they'll hopefully come together more once we see the applications. So just some wording here, which I brought up above there. So linear programming, also known as linear optimization, is a method used to try to maximize or minimize a quantity given by a linear equation. So that's our r equals 5x plus 10y up above, under certain restrictions or restraints. So the linear function is called the objective function. So that's what we're trying to minimize or maximize. And then there will be a system of linear inequalities, which will be called the restraints or constraints. That terminology switches back and forth. So the solution to the system of inequalities provides the feasible region. So when we start looking at these constraints, that's going to be graphing a system of linear inequalities. So that'll give us a region of a shaded area in our graph, just like we saw in our last videos. And we call this the feasible region. So it's like all of these possible solutions. But then because we want this specific minimum or maximum value, that's going to come from an x and y coordinate. And it's going to come from a vertex of this feasible region. So when we start shading these areas and look for where they overlap, what we might end up with is something that looks like a polygon. Like maybe we end up with something like this. And with the polygon, we have these vertices. So a vertex is a corner. So we want to evaluate these corners, which are kind of restricting this feasible region. And our minimum and maximum are going to be somewhere in there. So we're going to evaluate those coordinates. And we'll look at how to find which one is the minimum, maximum. So let's just go with an algebra example here, get away from the word problem, and just work with these pieces and see how we can graph these. So we want to maximize p equals 14x plus 9y. So that right there is our objective function. And what I'm going to do is pretty much ignore that function until I get this feasible region that I want to work with. Really, my focus is going to be on the constraints until I get that feasible region. So it's subject to the following constraints. X plus 6 is less than or equal to 9. 3x plus y is less than or equal to 15. And x is more than or equal to 0. Y is more than or equal to 0. This x more than or equal to 0, y more than or equal to 0 is going to come up quite a bit in this section, especially for our word problems. And that's setting the restriction that like x has to be positive, y has to be positive. So that means we have to be in the first quadrant. So with that, when I start making a grid here, I'm just going to focus on the first quadrant. So we're going to make a graph. And let's see, I'm going to be graphing. One second. Sorry, I'm going to change that first one. Says x plus 6 is less than or equal to 9. I want y in there, not 6. That was a little typo. So x plus y is less than or equal to 9. So that would be the same as graphing y is less than or equal to 9 minus x. So let's go ahead and get that graphing. And actually, I'll just go ahead and adjust the second equation too. So 3x plus y is less than or equal to 15. So y is less than or equal to 15 minus 3x. So let's see, for the y-axis, I want to graph up to 15 and 9. So I want these to be pretty accurate. I'm going to do jumps of 3 here and see how that works. No, I'm going to do jumps of 2. 2, 4, 6, 8, 10, 12, 14, 16, 18. I'll also show that, like, if a point isn't clear, how we can find it algebraically as well. But for now, I think that'll be good. And then along here, I'm just going to go jumps of 1, 2, 3 for the x-axis. Okay, so let's graph these linear equations. Linear inequalities. Y is less than or equal to 9 minus x. So we're at 9 and we have a slope of -1. So let's see, I'm going to go down 1, right 1. So just paying attention to the units that I used here. So down 1, right 1. Down 1, right 1. And if it's helpful, like, we could think of the x-intercept should be at 9. So what we could do is just graph that x-intercept there, and that's where we should be landing. It can be helpful to graph these dots in between, though, since those could end up being our intersection points. So we'll be graphing below that line. So maybe I'll just make a little note to myself that we're shading below that region. And then we have y is less than or equal to 15 minus 3x. So I'm going to have my y-intercept at 15. If it's helpful, you could solve for the x-intercept. Let's see, that would be 3x equals 15. So that's going to be at 5. Let's see if we can get our slope of 3 going just for accuracy. 3, 3. 1, 2, 3 over 1. Okay, then I can see my intersection point coming in at 3, 6, which is really nice because we'll need that value. All right. And with that one, we're graphing less than or equal to, so this is also below. And then, so with that, I'm just going to get rid of these arrows for where we're not overlapping. So we're ending up with this corner around the origin here. And then remember that we need y is more than or equal to 0 and x is more than or equal to 0. So this is where we're ending up with this polygon that's trapped between these two lines and the x and y axis. So if I shade in here, just let me grab my correct highlighter. In here, this is our feasible region. So solving that system of linear inequalities, this right here is our feasible region. So in that region are all the possible solutions that fit the constraints. But now what we want to do is look at our objective function. We want to maximize this p equals 14x. So we want to maximize p equals 14x plus 9y. And with that, the maximum is going to come from a vertex of this polygon. So because we're restricted in the first quadrant, one of our coordinates is going to be 0, 0. That's a corner of our feasible region. We're going to have, so we have those two y-intercepts, but the one that's on the edge of our feasible region is the smaller of the two, so that's going to be 0, 9. We have the intersection point of the two lines, which is happening at 3, 6. And then for the x-intercepts, we have the smaller of the two, which is 5, 0. So we want to evaluate those vertices that are these corners of our feasible region. So what I'm going to do is grab those coordinates and list them off to the side here. So we have 0, 0, 0, 9, 3, 6, 5, 0. And what we want to do is take each of those points and plug them into our objective functions. That p equals 14x plus 9y, I'm going to evaluate each of these. So at 0, 0, p would equal, well, now it's just all going to turn into 0, plugging that in. If I plug in 0, 9, let's see, we'd have 9 times 9, which is 81. At 3, 6, let's see, 14 times 3 plus 9 times 6. And that's going to be a 96. And at 5, 0, p equals 14 times 5, which is 70. So we have our corners. We plugged into the objective function for each, and our whole idea is that we want the maximum. So which of these maximizes p? Well, it's going to be the one that gives us the largest value for p. So you got p equals 96, and that came from the coordinate 3, 6, which means that 3, 6 is our solution. So we would say the maximum, so the 96 is our value that's coming out, so that's our maximum value. So the maximum value of 96 occurs when x equals 3 and y equals 6. And that's our final solution. All right, let's talk through these steps one more time, and let's just get kind of some steps that you're going to follow with each of these scenarios. And then when we get to word problems, part of it will be forming these equations here. So first thing we do is graph the constraints, which is going to be graphing a system of linear inequalities. Then that'll give us a feasible region, and we want to grab the vertices of that feasible region. And then we go to our objective function and plug in those vertices. And then depending on whether we want to minimize or maximize, find the one that's giving the minimum or maximum value, and that's going to link a coordinate and a value together to give you your final solution. We'll go through a lot more examples of this, but this will get us started. Oh, and with MyOpenMath, oh, and let's look at Desmos too. Sorry, all these ideas right at the end of how technology can help us. So with MyOpenMath, the solutions, it's going to say draw a polygon. So like for this case, I'm not going to do the one, it's going to take me too long to try to do that one. So you want to do side work, like on a separate piece of paper to get this feasible region going. So with this, where it's saying graph the feasible region has these corners 0, 0, 0, 9, 3, 6, 5, 0. So I'm going to do in MyOpenMath is to draw the polygon. I'm just going to graph those points. So 0, 0, 0, 9, 3, 6, and 5, 0. And then connect back to the origin, and that'll shade in a region in between those, and that'll be the feasible region. So when you have this polygon drawing tool, you won't have all this extra information that's in there. It's just thinking about this feasible region with those corner points, which is really what's important for solving our linear programming. Then in Desmos, to get a visual for this, what we can do is graph all of these. Like we can graph x plus y is less than or equal to 9. We can graph 3x plus y is less than or equal to 15. And then we'll have the x is more than or equal to 0, y is more than or equal to 0. And as you can see, it gets messy real quick, especially I'm super zoomed out. Let's zoom in. So we're doing is we have 4 shaded regions here. There's like red, green, blue, purple. And we are getting these spots. And what's nice about Desmos is it'll grab those key points for us so we can get those corners here and make sure we're on the right track. But seeing where all of them overlap can be really difficult. So what we could do, my little tip is switching all of the inequalities around. So like where x plus y is less than or equal to 9, I could rewrite that as more than or equal to 9. And 3x plus y is less than or equal to 15, changing that to more than or equal to 15. And x more than or equal to 0 is less than or equal to 0. Y more than or equal to, switch it. And what that'll do is by flipping all of the inequalities, instead of the shading being the overlap of all of the pieces, it reverses it, so it's the only thing that's not shaded in is the solution, which is a lot easier to see with all these different colors and the overlapping. Having just the blank space be the solution is so much easier. So when, again, Desmos will show us these key values coming through, and we could get our corner pieces there using Desmos or using it to double check our answers.